They call it green gold, a plant that can grow nearly a meter in a single day, mature in just 3 years, and store as much as 343 tons of CO2 per hectare. Bamboo's remarkable biology has begun a global race, billions in investment, cutting-edge farming with IoT sensors, entire forests transformed into flooring, textiles, and even bioplastics. But if bamboo is truly the future of sustainability, why do its eco-claims come with growing pains, high-tech risks, and debates no one wants to settle? From forest to fortune, how bamboo becomes eco-friendly. Gold isn't just about the plant, it's about the industry, the science, and the uneasy questions that start beneath the forest floor. What hidden cost comes with the boom? Bamboo stands apart in the plant kingdom for one simple reason: speed. Some species shoot upward by nearly a meter in a single day, reaching full height in just 3 years, a fraction of the time needed for most trees. But the real secret lies beneath the surface. Each stalk connects to a vast underground network of rhizomes, thick, woody roots that spread horizontally, sending up fresh shoots year after year. This living web allows a single planting to outlast generations, with new stems replacing the old in a seamless, self-renewing cycle. Unlike timber forests, where replanting is required after every harvest, a bamboo grove regenerates itself, slashing the need for intensive soil disturbance and chemical inputs. Bamboo's rapid growth isn't just a marvel of nature, it's a powerhouse for the climate. Over its lifetime, a well-managed stand can store between 344 and 950 tons of carbon dioxide per hectare, depending on species and conditions. Moso bamboo, native to China, is especially efficient, with top-performing groves rivaling or exceeding the carbon stocks of many hardwood forests. Annual sequestration rates run from 5 to 12 tons of carbon dioxide per hectare year after year, locking away carbon both above and below ground. The rhizome system plays a crucial role here, channeling carbon deep into the soil and building organic matter that remains even after harvest. This relentless cycle of growth, harvest, and regrowth transforms bamboo into a living carbon sink. In Brazil, new plantations have turned degraded cattle pastures into dense, green corridors, with soil, carbon, and biodiversity rising in tandem. In Asia, bamboo's ability to bind soil and retain water has helped stabilize hillsides and restore fertility to exhausted land. Each clump acts as a living sponge, soaking up rainfall and anchoring the earth, reducing erosion and runoff during heavy storms. The biological edge doesn't end with carbon. Bamboo's high yield, up to 60 tons per hectare annually, means more raw material from less land, easing pressure on native forests. And because the plant thrives without synthetic fertilizers or pesticides, it can be grown in regions where other crops fail, opening new opportunities for rural economies. As the world looks for ways to balance economic growth with environmental repair, bamboo's physiology offers a blueprint for abundance without depletion. The story of bamboo begins not with gadgets or factories, but with a plant that rewrites the rules of regeneration. On the outskirts of Lin'an, Zhejiang, Li Mei stands at the center of a bamboo grove transformed by technology. In her family's fields, dozens of slender metal probes rise from the soil, each one monitoring moisture, temperature, and nutrient levels in real time. 3 years ago, Li Mei invested in a network of IoT soil sensors and automated drip irrigation. The results have been dramatic. Yields are up by nearly 19%, and the once frequent blight of root rot has faded to a rare occurrence. Instead of watering entire hillsides by schedule, the system targets only the rows that need it, delivering just enough for healthy growth, even in the driest weeks of summer. Precision agriculture has changed daily life for Li Mei's crew. Armed with a phone or tablet, workers check dashboards that show which sections need attention. Watering cycles now run overnight, slashing daytime labor and minimizing evaporation. Fertilizer use has dropped too, as nutrients are delivered in carefully measured doses through the same drip lines. With fewer passes, by tractor, and less hand weeding, input costs have fallen, and the grove's water table remains stable even after a string of dry seasons. Disease management is another frontier. Rather than relying on broad-spectrum pesticides, Li Mei's farm uses biological fungicides and targeted biocontrols, deploying beneficial microbes and natural enemies against pests and pathogens. The sensor network alerts her to sudden changes in soil humidity or temperature, allowing early intervention before disease can spread. Fewer chemicals mean healthier soils and a safer environment for both workers and wildlife. The gains are visible in every corner of the grove. Bamboo stands taller and denser, with uniform culms ready for harvest. Each year, the farm produces more high-quality poles from the same acreage, providing a stable feedstock for the region's processing mills. For Li Mei, the shift to data-driven farming isn't just about bigger harvests. It's about resilience. With climate patterns growing less predictable, the ability to adapt quickly has become the farm's greatest asset. In the heart of China's bamboo belt, the ancient cycle of growth and regrowth now runs on sensors, algorithms, and local know-how, building a foundation for the next stage of bamboo's journey from forest to fortune. On a humid morning in May 2008, disaster struck the heart of China's bamboo belt. The Wenchuan earthquake sent shockwaves through Sichuan, toppling buildings, buckling roads, and plunging entire towns into darkness. At the Yongsan bamboo mill, plant manager Zhao faced a crisis that threatened not just the factory's future, but the livelihoods of hundreds. The main power grid was down, cell towers flickered, and 20,000 tons of freshly cut bamboo, enough to supply the region's mills for months, sat stacked and vulnerable. In the subtropical heat, every hour mattered. Without rapid drying, the culms would begin to ferment, turning to mush and inviting mold and insects that could wipe out the entire year's harvest. Zhao acted fast. With no time for debate, he ordered the backup generator rerouted from the main office to the old warehouse at the edge of the yard. Crews scrambled, unspooling thick cables by the light of cell phone lanterns. The warehouse, once used for storing tools and spare parts, became an emergency drying hall. Workers from nearby villages arrived by bicycle and on foot, forming teams to haul, stack, and arrange the bamboo in tight rows. Industrial fans, scavenged from the packaging line, roared to life, blasting warm air across the green culms. The process was rough and improvised, but it was the only hope of saving the crop. For 3 days and nights, Zhao and his crew worked in shifts, snatching meals and sleep on the warehouse floor. The air inside grew thick with the scent of fresh bamboo and sweat. Every few hours, a new problem surfaced. A jammed fan, a blown fuse, a leaking roof when the rains returned. But the workers pressed on, driven by the knowledge that the entire local supply chain depended on their success. If the bamboo spoiled, factories across the region would grind to a halt, paychecks would vanish, and families would go hungry. By the end of the week, the first loads of dried bamboo rolled out of the warehouse, bound for the processing lines. Factory logs show that nearly 90% of the threatened harvest was salvaged, an extraordinary feat under the circumstances. The emergency drying hall became a symbol of resilience, a reminder that even the most robust supply chains can be fragile when disaster strikes. Zhao's quick thinking and the community's determination preserved not just raw material, but the future of an entire region's bamboo industry. In the aftermath, calls for more robust processing infrastructure grew louder, setting the stage for a new era of investment and innovation in bamboo logistics. Inside the industrial heart of the bamboo revolution, the transformation from raw stock to high-performance material happens at a scale and speed that would have been unthinkable just a decade ago. At the entrance of a modern mill, trucks unload their cargo into a maze of robotic conveyors, each stalk scanned, sorted, and routed to its next destiny. Sensors measure diameter and density in milliseconds, assigning thick-walled culms to engineered flooring lines, while slender poles are diverted for chopsticks, panels, or pulp. In the main hall, automated splitters slice bamboo into precise strips. These pass through steam chambers where high-pressure jets sterilize and soften the fibers, removing sugars that would otherwise attract mold or insects. The next stop is the adhesive line, where chemistry takes center stage. Here, strips are coated with resins, urea formaldehyde for everyday panels, phenol formaldehyde for water-resistant boards, and MDI for the toughest strand-woven products. Each resin brings its own risks. Workers in this zone wear filtered masks and gloves, as even trace exposure to formaldehyde or phenol can cause respiratory and long-term health problems. Despite improved ventilation and resin capture systems, the industry faces growing pressure to adopt bio-based adhesives and reduce emissions. Engineered bamboo products are pressed under immense force, up to 120 tons per square meter, at temperatures exceeding 150 degrees Celsius. The result is a material harder than oak, with the flexibility to rival steel. But every step introduces new complexity. Silica, naturally present in bamboo, can block filters and erode machine parts, forcing costly shutdowns for cleaning and repairs. In one pilot facility, a month's production was halted after fine silica dust clogged the nanocellulose extraction line, highlighting the hidden technical obstacles of scaling up. Innovation, however, is relentless. At the University of Tennessee, a team of researchers has spent years refining a process to convert bamboo into nanocellulose, a lightweight, ultra-strong material with applications in bioplastics, medical devices, and even electronics. Their breakthroughs have drawn attention from industry giants and sparked intense debate over patents and intellectual property. Graduate students and faculty have filed competing claims on solvent-free extraction methods, each hoping to secure the next leap in sustainable materials. The stakes are high. Whoever controls the process could shape the future of green manufacturing for decades. Yet progress is never simple. Every new adhesive, each robotic upgrade, and every experimental process brings its own set of risks and trade-offs. Worker safety, resin emissions, and the environmental footprint of production remain under scrutiny. As the industry pushes forward, the promise of bamboo as eco-friendly gold depends not just on what happens in the forest, but on what unfolds behind factory walls, where science, engineering, and ethics collide. A single shipping container packed with bamboo flooring boards leaves the port of Qinzhou, Guangxi, bound for North Carolina. Inside, the cargo is anything but ordinary. Humidity and temperature sensors are embedded at 3 points along the load, transmitting data every hour. These readings are tracked by both the exporter and the U.S. importer, forming a digital trail that will follow the shipment across the Pacific. At the mill, each bundle passed a moisture test, with only culms below 10% moisture content cleared for export. Quality assurance teams sealed the container after a final inspection, marking it with a tamper-evident tag linked to a blockchain ledger. The journey is not without its obstacles. Midway through transit, a 2-week customs backlog at the Port of Los Angeles brings the container to a halt. During this period, external humidity spikes threaten to compromise the bamboo's integrity. Automated alerts flag a rising trend in internal moisture, prompting the importer's QA staff to request an inspection. Port workers trained in cold chain protocols intervene, venting the container briefly and restoring the internal climate. Data logs later confirm that the load remained within specification for fiber strength and color. Every checkpoint, departure, transfer, customs, and final delivery, requires a digital signature and a new round of testing. The container's journey is mapped in real time, with GPS logs and sensor data stored for audit. Out of thousands of containers shipped each year, more than 98% now arrive within spec, a dramatic improvement over the days when a single leak or delay could ruin an entire shipment. This level of traceability is now standard for premium bamboo products entering the US market. It's a system designed not just to prevent shrinkage and spoilage, but to satisfy the growing demand for environmental audits, ensuring that every board, panel, or chopstick can be traced from forest to factory to final destination. Brazilian field trials offer a glimpse of bamboo's environmental promise, yet also reveal the limits of simple success stories. Soil core samples from Minas Gerais show that where degraded pasture gave way to managed bamboo, organic carbon content rose steadily over 7 years, with deeper layers accumulating stable carbon fractions. Bird surveys in these same corridors recorded a surge in species richness, more nesting sites, more insect prey, more calls at dawn. But the numbers defy easy slogans. No peer-reviewed study confirms a universal 20% gain. Instead, the outcomes shift with local management, rainfall, and the mix of native plants woven among the bamboo. On the climate front, the optimism of carbon-neutral marketing faces a stubborn accounting gap. When Moso's flagship flooring line underwent a third-party audit in 2021, the findings were clear. Carbon emissions for shipments to Europe and the US ran 30% higher than advertised, once ocean freight, resin production, and coal-powered boilers entered the ledger. Life cycle assessments, often cited in promotional materials, sometimes omit key phases: shipping, end-of-life disposal, or the true mix of local grid electricity. The result? A product that is greener than plastic or steel, but not the climate panacea promised in glossy brochures. Labor conditions raise further questions. In Myanmar, wage ledgers reviewed by NGOs hint at irregular payments and safety lapses on Chinese-backed plantations, but confirmable data is scarce. Rural workers often lack formal contracts or clear recourse when pay falls short, and union organizers face obstacles ranging from bureaucratic delays to outright intimidation. Industry investors have responded with compliance offices and new codes of conduct, yet independent verification remains limited. Ecological surprises test even the most careful plans. In 2007, vast tracts of Melocanna baxifera flowered simultaneously across northeast India and Myanmar. The resulting seed glut triggered a rodent population explosion. Fields stripped bare, rice stores emptied, famine looming in villages that had depended on bamboo for both food and income. Scientists now monitor flowering cycles closely, but the lesson endures. A single plant's biology can ripple outward, reshaping entire landscapes and livelihoods. For every gain, carbon stored, soil healed, jobs created, there are questions that resist easy answers. The story of bamboo's rise is not just about what works, but about what remains uncertain, contested, and still unfolding. Bamboo matures in just 3 years, with documented cases storing up to 343 tons of carbon dioxide equivalent per hectare. This rapid growth and carbon capture have propelled bamboo from traditional rural uses to a multi-billion-dollar global industry. Evidence from Brazilian plantations shows a 20% gain in both soil carbon and bird populations. Yet, audits reveal that up to 30% of emissions can go unreported, and wage disputes in Myanmar between 2015 and 2023 highlight ongoing labor concerns. Some supply chain incidents, like the University of Tennessee's nanocellulose pilot blockage, remain incompletely documented. While 98% of shipped bamboo met quality standards after delays, questions about life cycle emissions and ecosystem impact continue. The record shows bamboo's potential for environmental and economic transformation, balanced by real-world complexities that demand ongoing scrutiny. Today, bamboo stands as both an eco-innovation and a work in progress, its future shaped as much by transparent data as by the ingenuity of those who cultivate and process it.